Good afternoon, Internet. I am Matt Buyak, and in this video, we'll be taking a look at the 38th problem from the Project Euler problem archive. Now, this problem asks us to find positive integers such that when we concatenate the first n multiples of that integer, we get a pan-digital number. And it defines a pan-digital number as a 9-digit number which contains the digits 1 through 9 exactly once each. Now, typically on this channel, I would show you how to solve this problem using basic programming techniques. And indeed, in the next video, that is what we will do. But in this video, we can actually solve this problem using pencil and paper and a little bit of clever logic. And before we get started, I would encourage, if you have any interest in logic puzzles or number puzzles more generally, maybe pause the video and give this a shot yourself before I go ahead and spoil everything. And with that out of the way, let's get into it. So as usual, we will copy our template directory to make our problem directory. But unlike usual, we will open our analysis file instead of our main.cpp. And let's begin with a few basic observations. So we'll say observation number 1. We know our final answer is going to have exactly 9 digits. And since our final answer is formed by concatenating our n multiples, we know that our n multiples have exactly 9 digits between them. So I should put this down on the next row. Okay. Observation number 2. N is less than 10. Now, it's given in the problem statement, though I didn't specifically mention it in the intro, that n has to be at least 2. But we can see that n also has to be less than 10 because each multiple has to have at least 1 digit. And if there were more than 9 multiples, we would definitely have more than 9 digits in total. And so n has to be less than 10. Observation number 3. And this one's going to be a little bit less obvious. Let's see, our nth multiple can have at most 1 more digit than our first multiple. And to see why this is, consider that when we multiply our first multiple by 10, the result has exactly 1 more digit. And since we have at most 9 multiples, we know that all of our multiples have to be smaller than that. And so they either have to have the same number of digits as our first multiple or 1 more than that. To give a specific example, so we'll say example 10 times 123 gives us 1,230. You'll note that 123 has 3 digits. 10 times that has 4 digits. And so we know that the first 9 multiples of 123 have to have either 3 or 4 digits. And so taking these observations together, we're looking for ways of adding up to 9 using only consecutive numbers. That is, we could use 2 and 3, or 3 and 4, or 4 and 5, but we couldn't use 3 and 5 because those are not consecutive. And to give another specific example, I'll say example, if we have 2 plus 2 plus 2 plus 3, that gives us 9. And so we could have a 4 multiples. We could have, let's say we could have n equals 4 with 3 2-digit multiples and 1 3-digit multiple. As one possibility. Now it turns out that there actually aren't that many ways of doing this. If we exclude 1-digit possibilities for just a moment, because there are many of them, we'll see that there are actually only 3 possibilities. So we can say excluding 1-digit 1-digit numbers, there are only 3 possibilities. The first we've already listed, so that's 2 plus 2 plus 2 plus 3 is equal to 9. The second would be 3 plus 3 plus 3 is equal to 9. And the last is 4 plus 5 is equal to 9. Now, what about those 1-digit numbers that I set aside just a moment ago? Well, rather than go through all the possible ways we can add up to 9 using 1 and 2, we can just try each of the 1-digit numbers. We can just try each 1-digit number. And so we'll do that now. So let's see. 1 gives us actually an answer. 1, 2, 3, 4, 5, 6, 7, 8, 9 is a pandigital number. It's the smallest pandigital number. It's not our answer, but we got to start somewhere. 2 gives us 2, 4, 6, 8, 1, 0. And unfortunately, that contains a 0. Not allowed. 3 gives us 3, 6, 9, 1, 2, 1, 5. Repeats the 1. 4 is going to give us 4, 8, 1, 2, 1, 6, which also repeats the 1. 5 is going to give us 5, 1, 0, contains a 0. 6 is going to give us 6, 1, 2, 1, 8, repeats the 1. 7 gives us 7, 1, 4, 2, 1, repeats the 1. You might be noticing a bit of a pattern here. 8 breaks that pattern slightly with 8, 1, 6, 2, 4, 3, 2, repeats the 2. And 9 actually gives us a second possible answer. We get 9, 1, 8, 2, 7, 3, 6, 4, 5. And actually, if we go back to the problem statement briefly, this is actually given as an example you'll see right here, which is a little bit unfortunate because this candidate answer turns out to be quite significant. But I didn't want to use the fact that they provided this as part of my solution. It's not too hard to discover in any case. But the reason this turns out to be a significant candidate answer is because it begins with a 9. So we'll say note, and in particular, because we're trying to maximize our answer, any larger pandigital number must also begin with a 9. And so either this is our answer, or there's another pan-digital number which also starts with a 9. And so we can say our answer must begin with a 9. Okay, so that means obviously our first multiple must begin with a 9. We'll say just therefore our first multiple must begin with a 9. And also our second multiple must begin with the digits 1 and 8. And the reason why the second digit of our second multiple can't be a 9 is because we've already used 9. We already put 9 in our first multiple. Okay, the other important observation, so we'll say important observation, is that our second multiple has to have one more digit than our first. So our second multiple has one more digit than our first. And that's just because by doubling our first multiple, that 9 carries over and adds an extra digit in the second multiple. But this is important because it actually eliminates most of the remaining possibilities. Therefore, in particular, you'll recall if we go back up here, our other possibilities were 2 plus 2 plus 3, 2 plus 2 plus 2 plus 3 is 9, 3 plus 3 plus 3 is 9, and 4 plus 5 is 9. But we just said that the first and second multiples can't have the same number of digits. And so this first possibility won't work. This second possibility won't work. We're only left with this last possibility as an option. Now, at this point, we don't know that there are any other solutions. It could be that this solution given down here, 918273645, is our solution. But this was given in the problem statement, so it seems a little bit unlikely that that would be our answer. Let's see. If there are any larger solutions, we must have n equals 2. Our first multiple must have 4 digits, and our second multiple must have 5. Okay, so now we can kind of start to make the outline of a solution here. We've got, a 9 with 3 empty slots, and then 1 8 with 3 empty slots. And we need to figure out where the other digits might go in these positions. And to start, we can think about which digits can possibly go in the first multiple and which have to go in the second multiple. And so we might, let's see, observation. We'll start with 5. 5 cannot go in the first multiple because the corresponding position in the second multiple would either be a 1 or a 0. Now we've already used 1. We can see in our sort of skeleton solution here, we've already used 1, and 0 is not allowed. And so 5 must go in the second multiple. 5 goes in the second multiple. Similarly, if we look at 4, 4, if you were to try to put it in the first multiple, would give you either an 8 or a 9 in the second multiple in that same position. And so 4 can't go in the first multiple. So 4 goes in the second multiple. And so we've got 9 in the first multiple, and 1, 8, 4, and 5 so far in the second multiple, though we don't know exactly where the 4 and 5 go. But we can ask what digits might be able to go above the 4 or the 5. So we'll say observation. The only digits which can go above 4 are 2 and 7. And that's just by basic arithmetic. I don't think it's too hard to see why that's the case. But we can make the same observation about 5. We can say observation. The only digits which can go above 5 are 2 and 7. And this means that, well, it means a couple of things. We'll say key result, 2 and 7 cannot go in the second multiple. And that's because if you were to try to put 2 or 7 in the second multiple, 4 and 5 would be left, one of the two would be left without a digit above it. There would be no digits that you could place in that position, which would be arithmetically correct. Let's see, and we'll say, and also either 2 is above 4 and 7 is above 5, or vice versa. And then we'll have another key result that follows from this, is that 3 and 6 must go together. So we'll say either 3 is above 6 or 6 is above 3. And that's because that's all that's left. We know that 2 and 4 go with 7 and 5 in some arrangement. The 1, 8, and 9 are already spoken for. So that leaves only 6 and 3 that have to go together in the same column. Now, we're starting to close in on our solution here. There aren't too many possibilities left. In fact, there are exactly 24. And we could go through and list all of those and check to see which actually work and find the largest one. But there's one more trick we can use to save ourselves a little bit of tedium. And that's to recall that we are trying to find the largest solution. So there may yet be multiple solutions that we could still form. Out of the 24 that I mentioned, maybe more than one of those are valid solutions. But we're only concerned with the largest one. And so really, we want to maximize the digit that's just to the right of the 9. And the reason is that when we concatenate our first multiple and our second multiple, that will be the most significant digit that we have yet to determine. But we can't make that digit too big. In fact, I mean, you can see if we tried to put a 6 in here, for example, well, this would then have to be a 9. But then we would have 2 9s, so that doesn't work. And any other large number here has the same problem, that we would end up with a second 9 rather than an 8. And so this digit has to be either 1, 2, 3, or 4. But we've already used the 1, and we've said that 4 and 5 have to go in the second multiple. And so we have this result. We'll say observation. The only possibilities for the second digit in the first multiple are 2 and 3. And since we're trying to maximize the value of our final answer, it makes sense to try 3 first. Now, there's no guarantee that there are any answers which have a 3 in the second position. But if we do find any, they will necessarily be larger than any which start with a 2. So let's just, we'll say note, any solution which begins 9, 3 will necessarily be larger than any solution which begins 9, 2. Okay, so going back up to our partial solution here, let's move this down to the end. We can try putting in a 3 here. Well, we already said that 3 and 6 have to go together, and so we know that 6 goes in there. But then we can use the same reasoning that we just used to limit the size of this digit, that is the second digit of our first multiple. We can use that same reasoning to limit the size of the third digit. And that's because, again, if you tried to put, for example, 7 in here, then you would get another 7 there. Or if you tried to put, well, I mean, we're out of large digits, but suppose you broke our earlier observation and tried to put a 5 there, it would be the same problem. And so you can't put any large digit in this position without breaking this 6 here. And we've already used 1 and 3. We know that 4 has to go in the second multiple, and so that leaves only 2. 2 has to go there. 7 we know has to go in the first multiple, so it has to go there. And completing the arithmetic, we get this answer. And if we take these and concatenate them, we get this as our candidate final answer. So let's go back to the archive here and open up our problem. Unfortunately, I am not signed in for whatever reason, so that's a bit anticlimactic. Give me just one moment here. Okay, and now we scroll down to our problem, and you'll see that that does, in fact, match our solution. So thank you very much for joining me for this video. As I mentioned, in the next video, we'll be solving this same problem using basic programming and C and C++. I do hope that you'll join me.